Okay, before I start what I plan to do today, let me explain the outline so that you understand the broader picture. Okay, here what we are going to do is we will use TensorFlow 2.0 functions to implement a simple learning model. That means it is going to learn from a set of values just to predict a, or I won't even say predicting, fitting a points which are actually generated for a particular line. So the model is going to take this different data points and then construct the equation of the line. Okay, so to start with, the model would assume that the line is maybe like this. Okay, it's a straight line. I'm not saying it's a linear line. Okay, don't assume that it is a order 2. It's a straight line, but it doesn't know the slope and the point of intersection of y-axis. So it doesn't know both. That means, let me say y is equal to mx plus c. You know that if m is positive, it will be like this, and if it is negative, it will be like this, a line. This is m is positive, and the value c, if it happens to be a positive value, it is intersecting that at this point. That means when x is equal to 0, we get y equal to c. So what we plan to do is, we do not know that the points which are given is actually matches to which particular line, okay, corresponding which line. So we assume a particular slope and particular constant intersection point, and then we train the model to learn from the points what is the actual line that these points represent. So that's a problem statement which we are going to write a program using the TensorFlow. I am not going to use intentionally any Keras API. Okay, as I told you earlier, Python is below, NumPy is on top of it. We learned in the last semester, we learned this in this current semester before midsem. Then I said that I gave you an introduction of what is a TensorFlow, how tensor runs through particular network. I gave an example. So TensorFlow is running on top of NumPy. On this, Keras is added on top of it. So why did they add this Keras API? This is to make our life simpler to define models. So this is going to in turn called TF. TF is actually tensors are implemented using NumPy arrays. NumPy of course is running on Python. So this is how it is whole thing is going. But most of the NumPy is not actually a bytecode generated. It is optimized to run on the hardware CPU directly. So it is written in C or C++. Most of them is in C, and we run it on CPU. That's why we get much better performance in NumPy than using the Python array, because Python arrays are actually implemented as Python objects, and it is running on a bytecode. Means bytecode is generated and then it runs on the virtual machine and then CPU. So I hope you understand the complexity on which things are sitting on, what APIs or implementation the other things are depending on. So we are going to use TF now to start with, not Keras APIs, because it is actually abstracting out lots of things which are implemented in TensorFlow. And one more most important thing is we are using 2.0. Okay, for sure, please remember that. And my Anaconda environment is TF 2.0 CLS class. Okay, I think this overview is enough for us to start off with. Now, before that, I would like to tell you one more thing. Okay, In neural network, actually I mentioned that when I say that perceptron or a neuron is implemented using a bias and then different weights to the input, and then we have some transition function which could be a sigmoid or a rectified linear, whatever may be the function. Now these weights are multiplied with the tensor which is coming in as an input. Okay, this is W2, W3. Okay, so they all get added, all the weights and the input, and the bias is also added to that. Then a transition function is applied to get an output. Okay, that is a normal implementation of neuron or a perceptron in to implement a real neural network. Now here, if you remember what I mentioned about neural network is we have so many layers of neurons. Assume that this is one input and this is the output. What happens is this input is given, and this, if it is a dense layer, all the previous layers nodes will be connected to every other node. Okay, and everyone will have some weights, and finally all the outputs will be again, everything is, there is a weight here. Okay, and then output is predicted. Now this is a, okay, I assume that everything is connected. It's a dense network. Now what is happening is at each node level the operations are happening. That means multiplying the weight with the input and then adding a bias. Every node is having a separate bias. Okay, and then each of them having some transition function. Now how are we training a network? We have to train a network with a known set of values. So we know input and we also know the output, what is expected for a particular input. So during the training phase, what we do is we pass the input. This neural network, these nodes are all assuming something to start with, and then the input is fed to it because it is not trained now to start with. They have some random values as a weight and bias. So they give you some output, and we find the difference between the output, what we get out of this particular network. I'll call this as a predicted value, which is predicted by the network. So predicted value minus actual value, because we know for a particular input I1 what is the expected output VO1, and we also know what we are getting as a predicted value 1, and then this difference is what is loss function. Okay, this is a loss function or a cost function. How we compute the difference, whether we do a mean arithmetic or arithmetic, what kind of MSc or MAE, I'll cover about it. We find the error. This is the error currently, that the network is deviating from actual output. Then what happens is this loss is propagated up, which is called the back propagation. Okay, to adjust the bias and the weights of each of the nodes as it progresses up based on the loss. So this we do for one data, and then we again give another data. We get some other output data with the updated network. We get O2, then again new loss will be found, and we do the same thing. Okay, so as this back propagation happens, we try to make sure that all the weights are adjusted in such a way that when unknown value Ix is given, the Ox what is coming out is not much different from predicted value, the actual X. Okay, for this input what should be the actual value will be closer to that. Now this is actually about the neural network where this philosophy is used, and how do we find out whether how to adjust these values. We find the gradient of these constants. Okay, gradient, the change, whether if I take this value, if I want to reduce the loss, how do I change the weights such that I get the correct output. Okay, so we find the slope of the change that is we need. Okay, and then we adjust it. I will explain it shortly. Now Before I go into the details of this neural network and implementation, I want to take only one value. Assume that it is like a node, which is nothing but a line model. I want to adjust it. So my input is, I said that this is the line. I consider this to be the weight. Okay. This is the weight. And I consider this to be a bias. Okay. This we are just doing what we did at the different node levels in a neural network. We are doing it for one particular node. You can assume it to be a node. But there is no transition function here as such. So we, instead of one x value, we may use a set of x values. Okay. Initially we assume some a slope and some b, some constant bias, and then we have a original equation. I written it as 2x plus 0.9. This is y equal to 2x plus 0.9 is the actual line I am want to implement it. I want to model the numbers. So initially I may assume some value, maybe a equal to some 20, b is equal to some 30, maybe whatever. But I want to get to this value, okay, based on the input that I give. That is our goal now. So we are trying to fine tune the weight, which is nothing but the slope in our case, and the bias, which is nothing but the constant intercept of the line with the y-axis. We consider to be a weight and bias, and we use the same gradient and we do the back propagation. Here there is nothing much to propagate. It's only one value. We will do it because we are not going into multiple layers, but we do only one and try to run multiple times on the data and bring down the loss and stop somewhere. So now you know that if you are running through a training, it's called epoch. Okay, a particular epoch is one set of input is given and then we train it. In our case, in this example, we are going to give one input. For us, it's like Brahma and our life is different, right? The number of years that we spend is equal to 1 day for Brahma. So in normal neural network, the epochs may be multiple data is given and then we train it and then we change the weights once in a epoch. But here for every data, we are going to do that. When we are feeding in the data, we take one data, we train it because we are only training one weight and then one bias. And then we again give one more data and then we train it. So I'm going to measure the loss as we train it. Okay. This is the code that I have given you now. Well, let us now understand stage by stage what we want to do. Okay. I may not be able to completely explain the code because you have class at 5 o'clock. So wherever we go, we'll stop there and then whatever we can complete. And then tomorrow I will complete the remaining explanation. But anyway, code is there. You can run it and understand it yourself. But I will explain it in detail about what is happening. And then we will do some exercise tomorrow. Okay. In the same code, I will ask you to modify something to implement some other model. Okay. Now this is the overview of what we are going to do. Is there any doubts before we start off? Okay, nothing else so far. So let us start off something, because I hope most of these things you may be knowing it because you are already completed many courses on AI and neural network. We are going to see some implementation if you have not seen it earlier. Okay, now it's a linear regression model. We are going to start with the regression algorithm. Our goal is to build a simple model to predict the values of dependent variable, which is y, from the values of one independent variable, which is x. The relationship between these two variables is a linear. I explained it. The goal of this exercise is to use TF, okay, not Keras or any other API. We are going to use TensorFlow to understand two most important concepts, either you can call it as a loss function or a cost function, and then gradient descent algorithm. Now, for anything to train, even if you want to train one single node, we need a set of data, right? So let us see how are we going to generate the data. The first step is to create synthetic data, because we are going to artificially generate a data. We assume some line and then we generate a data. This equation, this is the equation I am assuming it to be regression equation. Okay. regression equation means we want to predict, given a x, what is the y value if the model is supposed to implement this equation. Okay, this is called regression. Now what is regression? I'm sure you know it. Okay, now relationship between x and y is linear and a and b are constants, and the slope is equivalent to weight. Okay, and the bias is equal to b. Okay, in this case we are assuming a weight is always something which is multiplied with an input, so we call it as a weight, and bias is something either it's like don't assume that bias is always addition, it could be negative also, but in our case we are assuming it to be a plus 0.9. Now to test our algorithm, I am going to generate some line points. Now this is the x-axis, up to from 0 to 3 we have some values, and then y is generated like this. This is applied on top of this equation. Now you may wonder, if I had really used this equation, I will not get the distribution around this point. It should have been a single line going through it. Now why am I getting a distributed line points? That is because I have intentionally made the values distributed around the line that I am interested in. Okay, let me explain why I did. I did that using the normal distribution. Two reasons. One is the points that you get, that is x, and then we get y from there. Okay, but most of the time what happens, the measurement that we have in any real life sensors, there will be a noise in it, so you are not going to get a pure input, or you are not going to be able to get the output also as pure as what is given as an input. So everywhere the system is having some stochastic behavior, wherein we don't assume the values to be exactly same as what we expect to have. So our model also should not exactly trained on that. Let me give a very rough example. In sometimes parents, okay, our parents, we are child, our parents do not give us all the comfort that we need. Okay, they don't give you pampering. We call it as pampering, right? If you pamper your child so much, then what happens is the child cannot live in the real world, because the real world is not as good as what the parents are giving it to the child. So our model also should be like that. We have to train it to be ready for handling the real life scenario. So we don't want to give it exactly the input that we want to train on. Okay, we want to train on a rough scenario that the model is ready to face the real world when it comes to the noisy scenario wherein the inputs are not as expected as it could be. So that is what is called overfitting. Okay, if you are pampering the child, you are overfitting the child. Okay, similarly overfitting the model, if you give the actual input exactly what is expected of for a line, or no, the model is going to be overfitting the value. I'll explain you what I mean by overfitting. So we are going to add some little bit of noise to the input while training the node or training the model. Okay, so now what is overfitting? Let me explain. This is the example of overfitting. Suppose your model is so accurate. This is for a classification problem, not for a regression problem. There are two kinds of inputs, this and this, and then we don't want the model to be so accurate that it covers everything so accurately in real life, because we want the model to be like this. Maybe one or two can be here, or maybe some circle could be here. It should more or less capture the behavior of this real life scenario, because if you do a overfitting, it could be because this may be a noise outlier. It could be outlier. So we are overdoing it here, and actually what is should be maybe some value which is supposed to be captured as this category our model will not catch it. Okay, if suppose some input is here, it will not catch it. So we want the model to be not as complex as this, which is not good. This is simple model because we are having a great, graceful changes to the border. Okay, but we don't want so simple like a single straight line. Okay, that is also not good. This is underfitting. So this is called underfitting, this is called overfitting. We want the model to be here. Now what are the advantages of having it here? The training the model will be much easier because you don't have to be so accurate in terms of coming up with a model which actually mimic this particular shape of this. Okay, and it also handles for some outliers. It could be some outliers also, it may not be actually the input. So noisy environment. So that is the reason we want to the model to be here and not here. Here it is too approximate, it is not, it's like a useless model. It is very easy to construct it, but it's useless. This is very complex to construct, but it is also not good. We want something in between. Okay, this is the appropriate fitting of the model. So avoid both overfit and underfit. If we don't train our model using random data, it may somehow memorize the relationship and lose the ability to predict correctly. Okay, that's what I'm saying, that in real life scenario it is going to be noisy, so you need to take care of naturally predicting the output, so that if you give an unseen data, it will be able to predict it properly. In real life, the data that we get is expected to be noisy. We want our model not to be either overfit, which is not realistic in terms of implementation and time consumed in terms of building a model, as well as the complexity of the model that you come up with will be much more, and which is useless. Okay, and we don't want underfit also. That means the model is too simple and generic. This is like this. We don't want both of them. I hope this is clear to you why we want this. Now how do you implement it? Now we want a loss function. We want to evaluate our model. We need to compare it with something, right? We need to know whether how far whether model is behaving, whether how bad it is or how good it is. So we need to have some cost function or a loss function. So it is a method of evaluating how well our specific algorithm models a given set of data. So our algorithm means how we implement it, what equation we use to implement the model, or how many layers we have, whether dense layer or what is the kind of properties of the model. Okay, how good it is in terms of matching with our actual model. So if the predictions deviate too much from the actual values, the loss function output will be more, otherwise it will be less. So that is the error output what we get. So we use some optimization. Okay, basically training a model is a optimization activity. We use gradient descent, I will talk about it, to fine tune the model based on the output from the loss function. So we evaluate the model based on the loss function output, what it is giving based on the current state of the model. Okay, we give input and then we take output. Okay, output, and then we see actual output also we have for this input, and we train it. We use the loss function to train the model, and then again give another input and see if there is any improvement. Okay, hopefully if you are training it properly, it should keep improving. The loss functions should give you output which is coming down. So the loss value will be like this, and then it will start coming down here. Okay, this is epoch. This is as and when you keep training it, the model becomes more closer to the actual model. So loss will come down. Now how long you go training it? See, based on the limitation of the model you have, you will not be able to improve your loss beyond some point. So there is no point in keep on training the network when you know that it's not going to improve. So you have to have some idea of when to stop the training. If suppose you see that it is like this, the error is some 0.2 and it is not improving, then okay, you may say that okay, 500 training points are enough, I stop it. But you are not happy with 0.2. Now what do you do? I want the error to be 0.1, but you are telling me that I need to stop it here because it is not improving. Then what you should do, you have to go back to your design change the model. Suppose you had a maybe 16 nodes and then 2 layers, maybe add more layers or more nodes, okay, and then try to do it. Maybe with that you will come down on the loss. So if the loss is not coming down after a few epochs, either you should be happy with what you get. If you are not happy, you should change the model. See, it is similarly what you do every semester. You work for maybe 8 hours in a day, and then end of the semester you see your CGPA. Either you should be happy with that or you should change the model. Okay, 8 hours. If CGPA is not good and you want to improve it, if you use the same model here, it is more or less going to be the same. So if you want to change the CGPA to something more, you need to change the model here. Maybe put in more effort, be smart, try to read more and practice, and try to improve it. So this is like this. If suppose you are not happy with 0.2 loss, you cannot keep on improving, increasing the epochs. You are not going to have anything more. So you need to change the way you work. So you change the model to do that. So that's how you normally train the model and how to use the values I'm telling you, so that I want you to intuitively do it. If you understand well, you will have a clarity on what to change to get what you want. So this is the loss function. You know about local minima and global minima. So when you start looking at the slope, you want to see that the slope is the error. Okay, as the slope is going down, you are going to hit on a place wherein you are having an optimized value. But the problem is you may hit a local minima where you assume that this thing is not improving, and you assume that this is the best result that you can have, but actually the best result would have been here. Now how do you do that? How do you know that you are not caught in a local minima and then you get a global minima? That is where you need to do two things. The loss function what you consider may not be good enough. It one thing is, okay, so you need to change the loss function, maybe change the error value, how you compute, maybe instead of mean square error, mean absolute error, or some other things you need to do. So there are multiple factors which are involved in terms of changing your loss function based on the algorithm that you have, the line equation or whatever. So whatever model you are trying to build, okay, that is one. Another one is the loss function is actually should help you to compute the derivative. Because why do we need to compute derivative? Because we want to find the slope, dy by dx. Unless you find the slope and the slope is either going down or going up, you will not know whether modifying the particular coefficient or a weight or a bias will bring down the loss still further down or will it increase it. So you should know the direction of the movement of the values. Okay, the slope you need to compute, and then the direction of the slope, whether it is positive or negative. Again, it depends on the loss function. Okay, maybe you may have a loss function which is like this, then you may be looking for a global maxima or a global minima. It depends on what you are looking for. It's not always same. You should understand the what you are looking actually, whether you want to have a higher output or a lower output. So in our case, we are trying to find out the error in it. So error means the difference between actual value and the predicted value of y. So we want this to be as minimum as possible. So I'm showing you this picture, which is more or less what we are trying to do. Then confidence on the predictions, how far the predictions are good. Based on that, the loss function could be changed. And then the percentage of outliers, that also makes a impact on how do you decide whether you ignore the outliers or you want to actually consider the outliers. Okay, outliers, you know that it is something which is too far from the actual input value, expected input value. So the loss function is different based on the machine learning problem that you have. Either it's a regression or classification. Okay, classification model is what I showed you in the overfit or underfit. But we are going to bother about regression. So let us come to the classification later on. So there are methods, mean square error, which you might have heard. This is actually finding the actual value with the predicted value you find the square of it, because we want the absolute error and not the whether we are not bothered about whether the error is positive or negative in this case, because we are adding up multiple errors and then finding the mean of it. Okay, so in that case we want only the absolute value. So we are not deciding based on one input, so we are having multiple inputs and then we add all the errors to find out how good the model currently is. Okay, so I will explain when the code I explain, it will become much more clearer than what you see here. So it's called mean square error is a function, loss function. Okay, it just finds the mean square of all the input that have been given and the predicted output of those inputs for a given model. Okay, so let me explain what I mean by that. A model is keep on improving on every epoch, right? So in one epoch, what we do, we give multiple input. Okay, we are not only stopping with one x value, x to x 120 maybe samples, and then I get y predicted value, y1 to y predicted values, y1 to y20. Then we compute the difference of these two and mean of that for a given model value. Okay, for a given value wx and base bias x, and then based on the loss function output we go and modify it. So it's not that we do one particular input and then one output and see the error and we go and modify it. No, in this, in one single epoch also, epoch here means how often you modify the model. Okay, so it is not something to do with the data. Suppose epoch 1 and 2, 3, 4, you will modify the model weights and base bias on every epoch. In between, you will run different input. Okay, you will give different input, not only single input. We give multiple input and multiple output. Then we do this because n is the number of samples. So we give that many every iteration. We give that n number of input on that particular state of the model. Okay, every time the model is in one state and we give all the input that we have, we know all the actual output for all this input, but the predicted value will be different on every iteration because we are modifying the weight every iteration. On every epoch we are modifying it, so you are expected to get a different loss value, which is nothing but a mean square error. Okay, remember, it is not one input to one output, it is a set of input to set of predicted output. So there is one more loss function which is MAE, mean absolute error, where we find the absolute value only, we don't square it. Now what is the difference between squaring and not doing it? If you do a squaring, you know that the graph will be like a parabola, y equal to, for ax kind of, it's a square value, whereas here it's a linear value which is like this if it is changing like this. Now the problem with the each of them is different. Okay, suppose if you find a error and then square it, the error is amplified. Okay, whatever error is there, that value is getting amplified because you are squaring it, whereas here it is just a error and then you are averaging it out. So outliers, if there are outliers, that means one outlier is there. Outlier means one data which is little farther away from the input, or one output whatever is predicted is too high, the difference will be very high and that will get amplified with the multiplication, squaring. So when you average it out, the MSE will be very high. Okay, for one, because of if your data has multiple outliers, your MSE is going to be high, and your model is going to be assuming that there is a huge error and it is going to modify a lot in terms of the values of the model. Okay, so it depends on whether your data has more outliers or not. Using the squared error is easier to solve, but using absolute error is more robust to outliers because we are treating these outliers in a normalized way here, not amplifying it. So it is robust, means the model changes happening to the model is not too high if the outliers exist in your data. Okay, whereas it will not be the case when you have a MSE. So it depends on whether to choose MSE or MAE. You need to whether you are very very particular about having outliers in, allowing outliers in your data or not. Suppose if you are very sensitive, you want the model to be very sensitive to outliers, you need to have MSC kind of a loss function, so that it is amplified, the output outliers are amplified, and the model is given advance notice that you catch, you take care of updating your model, that these outliers are taken into consideration for changing the model values. Okay, so that's what I'm saying, how robust it is. Okay, whereas MSC is very sensitive to outliers because it is squaring it. But the problem with MA is the gradient is same throughout. What I mean by that is, suppose if you have an error which is happening here, the difference in the error could be same, but the loss value is not changing so much. Okay, so it doesn't reflect, the slope is same. Okay, it doesn't matter where exactly, the slope is the same, whether you are finding the difference in values at the very top level, the model is coming down. Okay, the error is going down, the model is coming down, the slope remains the same. So whether the error is huge or not, the model MAE loss function doesn't give you output according to the place where you are. Whereas if you see here, the slope is little high here, whereas the slope is little low here. That means as you come closer to the actual value, the error is reducing, your loss function also is giving you a lower value. So MSC is actually smoother in terms of making your model behave according to the changes happening in the way the model is done. Okay, suppose if model is already converging, MSC will highlight it, whereas in MAE the model is, whether it is converged or not, you will not be able to know, because the loss function more or less happens to be the same. Okay, the value, if you see, it is still not too much of difference is there, the slope is same. So I'm not going to too much details, I'm sure you know more than me. Okay, fine, that is what is about loss function. Now finally, one about optimization, which is done by doing a gradient descent, which you might have already studied a lot about it. So optimization is most important. Now you found the loss. Now based on the loss value, either you might have used MAE or MSE, you found the loss value. Now you should know how do I change the model. So that is what is done by the optimization step, which is nothing but either use a gradient descent or a stochastic gradient descent algorithm to modify the model. Now this is what is called, another name for this is the back propagation, that based on the slope you find the loss, and then you go and update the weights and the biases in the model, different coefficients in the model, that you nullify the loss, so that if I make these changes, whatever is the current loss is reduced. Okay, that is how you do. To do that, you want to find the gradient, which is nothing but the differentiation of the value. So GD is used, find the parameters, values of coefficients of a function that minimizes the cost function. So what you want to do is, I want the loss to be minimum, okay, or maximum. Okay, you call it as a loss, then it should be minimum. Okay, somewhere you want to maximize the output. Okay, let us assume that we are calling it as a loss, so we want the loss to be minimum. So in that case, what we want to do, we want to adjust the coefficient in such a way that the loss is minimum. Okay, so that is what is the intent of the gradient descent. Now it is like a bowl where what is the current model value is here, and you compute the slope, and when you update it with the different values, then the loss function would have come down. So this is actually the graph of the loss function. Okay, loss function is traversing like this, and it is we are trying to go to the minimum. Okay, by adjusting the model, we want to, next iteration we want to see that loss has come down. And another word might have heard about the convex function. Convex function is nothing but, suppose if you have a points, okay, a convex function is something which is between the line, between the points you have, all other points are below the line. Okay, that is called convex. If you intersect any point, you will see that the remaining the curve, the between the points of intersection, all other points between them will be the below the line. That is called a convex function. Parabola is a good example, and even a circle, if you see, no, it will be below it. Okay. Okay. So I hope this is clear. What is a convex function? So there are some differences in terms of whether loss function is a convex function or not. The behavior is different for ML. So I am not going into the details of them. So the bottom of the bowl is the cost of the best set of coefficient, that minimum of the loss function. Okay. The goal is to continue to try to different values for the coefficient by evaluating their cost and choose a new coefficient that have slightly better lower cost. So we want to settle down at the global minima. Repeating this process enough times. Okay. So when changing the coefficient does not result in reduction in the loss, that is what I mentioned. When the losses continue to be the same, the algorithm would know that it has reached the bottom of the loss function. Okay. Remember, this has reached the bottom of the loss function for a given model. Okay, for a given model, because you cannot reach beyond some point unless you want to change the model. You cannot make it better even if you train it n number of times or infinite number of times. So now one more thing is, whatever reached minima, whether it is a global minima or local minima, how do you know? So that is where the stochastic gradient comes into picture. Now let me explain. When you have, this is a bowl kind of a thing, loss function. Suppose if you are taking the points in the order, in some order, okay, you are going to find the gradient and then you are going to go down like this. Okay. Now suppose all your points what you choose is always not in a random case, but you are doing it in a very sequential manner. You are going to be taking more time to reach the minimum. Okay. So what is expected of is, you want to reach the minimum. You might have heard about the, I forget the AI, random walk. Yeah, random walk. You might have heard about the random walk. Okay. Wherein you want to avoid the local minima by picking up the values randomly, so that you jump out of this slope. Okay, because if you are continue to get the actual adjacent values, you are going to get caught here, and then you will not be able to come out of this local minima, because if you find the slope, both will be higher and you are stuck here. So you want to come out of it and then find a, maybe I don't know which is local here. Okay, I'll assume that this is the global minima. If you want to come here, you need to choose a point which is at random, so that you get a loss function which is lower than what you had earlier. So that is what is called a stochastic gradient descent, wherein you get the input, feed the input in a random fashion, that you don't get stuck in a local minima. Okay. Which is also good point to come faster to your global minima. So it improves your time of convergence, and it avoids you getting caught in a local minima. So the basic HGD are the following: some random value as coefficient to start with, and then loss function is computed. You find the cost of the for a given coefficient, what is the loss cost function, find the derivative, that is the error, and then you find a difference. Now what you do, you are changing the coefficient based on the delta that you found. Now you are multiplying it with some alpha. What is this alpha? See, you found some error. Okay, maybe a error means delta. Okay, between the predicted value and the actual value. But because you are having a stochastic input, and whatever you are actually modifying the model based on the error, could be that it is one of the outlier data that you have taken. Okay, so you should not take the delta as it is. The problem is, you should not, sometimes they say that, if you are investing somewhere, don't invest huge money when you are doing it for the first time, right? To try to sample it, try to see whether the company is doing well initially, and then start investing more. So when you have a delta value, don't take it with the face value. Okay, try to control how much you take this, how much of this you believe to change your coefficient. Okay, that is what is the confidence level you have on the delta. So this alpha gives you some control, which is nothing but the rate. Okay, loss rate, which is called loss rate. You don't want to change based on one delta everything about the coefficient. So you want to take a sample of it. Maybe I will take it with a pinch of salt. Okay, so that I modify the coefficient only a little bit. Okay, maybe this delta is totally a wrong value. In that case, the changes what I have done, I can come out of it very fast. But if I believed it and then I invested all the money into that, I am gone. Okay, so invest small amount. So you don't delta, don't believe too much. Try to take a sample of it and try to update your coefficient. If that happens to be the same, then you will finally be going towards the right direction. So it actually takes care of two things. One is you are not making a wrong guess based on the input, updating the model. So that is how you learning rate is important. Because even when I'm telling you, when you look at the internet and try to learn about some concepts, sometimes what you get in the internet may not be the correct one. So you need to take it with a pinch of salt. Any input you get, okay, then you learn on your own, and that's the best way to finally come to a conclusion that what you learn is good. So your cost function will gradually go down and you will get a good model finally. Okay, that's what I wanted to show you today. I don't know whether my class is over with that itself. Oh, okay. Okay, guys. I think I maybe explained more. I'm not sure whether it was needed or not. What do I do? 5 minutes I will take. I will just tell you a overview of the code, and then we will stop. Anyway, you have the code with you. See, what I am doing is initial data. We are okay. It's very. I don't want to do it very fast here. I want to take any questions. You can go through the code yourself if you have time and energy, interest. I'm sorry I couldn't show you the code, but tomorrow we will completely see the code and then we will do some exercise here. Any questions, guys? First of all, I want to ask you whether should I explain this much or maybe I should cut down on this, because you might have already heard all this, I think. Let me know, should I theory be reduced or not? Theory to be reduced. Yes means reduced, or no means no reduced. Can you tell me, somebody? Oh no, okay. Because I don't want explain something which you already know. Okay, so many no's are coming. Okay, so I want you guys to tell me, if you have doubts, please ask me. Okay, I may not be able to answer everything, but at least I can come back also. But one thing I'll tell you, that why I spent more time on explaining the theory is it is very interesting. Okay, working on models and actually implementing it. But if you do not have the fundamentals strong, I tell you, is scary, very very scary. Okay, you need to have not only the theory behind what you learn. Okay, not only the theory is one thing, plus your language skill. Language means not I am talking about English and Hindi. Okay, I'm talking about the numpys and the TensorFlow. That knowledge also is important, because this is how you are going to express your theory into the model. Okay, so you will become good only if you have good knowledge on this. I'm not talking about being a very good in linear algebra or something. Decent enough knowledge is okay, the basic understanding, and then a good understanding of the language, or try to find out what is happening underneath. At least you should know how to find out, so that you can finally be successful in realizing a model which exactly meets your requirement. Okay, playing around with this is really interesting, and it will clear out so many of the doubts you have. That's why intentionally I am explaining this model implementing using TensorFlow, because if I go to Keras, it will say optimizer and then gradient, and it will go very top level. You will miss out on the interior details. So if you understand this code, I'm telling you, tomorrow I'll explain in detail. I'm pretty sure any model you can work on, and you will be having a thorough knowledge on what to control, how to control. You will have a clarity. Okay, so I will stop here because you have long classes following. So, and if you don't have any questions, we can stop. Tomorrow, come with a ready with the environment. I will give you a small problem also to implement after I explain this code, so that you get clarity. Okay, and one more thing I want to tell you, what I want to tell you. Okay, wait a minute, I'll do one job at a time. Okay, I was very strict on no, don't submit the lab immediately and all that. Okay, I'm not actually like that. So my intent is to make you learn. So I'm not going to put any limit on, but the problem is, you otherwise you will keep on accumulating on your to-do list. So if suppose we have a lab on Tuesday, maybe I will give a deadline till Friday. Okay, you have time to, but don't stretch it too much, because the next lab will come on the next Tuesday. So I will try to put some implementation and then ask you to submit on Friday, and then I will give you the my implementation of the same. Okay, I did not do that for the last lab because that is also required, so that you know what is expected of you. So I will give my implementation on maybe Saturday or something. Okay, so do one thing, let me tell you, doing is learning. Do it yourself, write programs, then only you will have confidence on whatever you learned in theory. Okay, so I believe in that. Okay, if you make a model on TF, does it have less overhead than Keras? um Not really, actually. Keras, they would have done much better than you. Okay, I'm sure these people are very smart and they would do much better job in terms. Actually, it is making your life easier in implementing it. In fact, if you do it yourself in TensorFlow, only you will do it inefficiently. It is similar to asking one question like, if you are too good in it, no, you are too good in implementing it, you may do a better job than Keras. Okay, let me give an example and stop. TensorFlow is below and Keras is implementing using TensorFlow. If you are too good in TensorFlow, okay, if you are too good, then you may do better than Keras. Otherwise, you will not. One good example is asking a question whether should I write a code in C or assembly, right? Generally, if you are too good in your assembly of a processor architecture, you will do a better programming than what the compiler generates. But most of the time it looks like these guys will do a better job, so we land up in doing in C. So to answer your question, if you want to really optimize something and you are an expert in TensorFlow, go with it. Otherwise, live with Keras. Okay, bye bye, see you tomorrow. Thank you. What pipeline will be used to get the model into microcontroller? I don't know, somebody has dropped off already. Okay, let me explain what I plan to do. Do you have time? Okay, just a simple thing. See, we have a TensorFlow or Keras. We build a model. Okay, then what I do is I am going to take a sine wave generation. Okay, after this line generation, we will take a sine wave generation, and then I have written a code to extract the weights and the biases of the model that you build, a neural network. Okay, and then I have a C code which is actually inferencing the model. Okay, whatever the layers you have, same thing is assumed here in the C model, and that is what is going to be run on ESP32. Okay, this is one thing. That means actual model, okay, TensorFlow model or whatever, the neural network, we will extract the weights and biases of all the nodes and then put it in a C header file and build it on Arduino Uno IDE and run it on ESP32. This is one step, okay. And then we plot the output here on ESP32. Second step is take the TensorFlow model, make it TF light, okay, and then generate the hex file from here, okay, which is a TF light format, okay, TF light format. Then run a inference engine. Inference is a small inference engine which is there part of the Google, they have given it, okay. We are not allowed to extract the weights and things here. We have to believe in their own inference engine which is running on ESP32 using the TF light model and then run it on ESP32. So these are the two steps we will do, okay. One is extracting the actual weight and the biases of the model. Second one is convert it into TF light model and then use it on ESP32. So these two I plan to do, and then it is for regression we will do for sine wave. If possible, we will see whether classification thing can be taken later on, okay. Okay guys, enough, bye bye.